We're starting. Okay, we're live. So hello, everyone. Welcome to our virtual field trip. My name's Gina Veramo, and I'm the outreach coordinator for NOVA. I'm broadcasting live from Boston, Massachusetts, where we're joined by middle and high school classrooms across the country. There's more than 20 classrooms watching us all across the country, all different grades, all different classes. And we just want to thank the Missoula Fire Sciences Laboratory for taking the time to be with us this morning. We're really excited to have you. So before I pass it off to y'all to give your presentation, I just have a couple of housekeeping notes before we begin. So I would love if you could keep your microphones muted if you're not asking a question currently, so we can make sure we can hear our presenters speak. So if you or your students have a question at any point during the field trip, please share them in the chat feature with your school name and location. When it's time for Q&A, I will read your school location out loud, and then that's when you can unmute your microphone and ask your question. So have the student approach the microphone, and you can ask the scientist directly. If you're watching on YouTube, you can leave your questions in the chat box on the right-hand side. And we'll try to answer as many questions as possible after Mark and Sarah's presentation. So with that, I'm going to turn it over to Dr. Sarah McAllister and Dr. Mark Finney, who study wildlife behavior or wildfire behavior and how wildfires spread at the USDA Forest Service Rocky Mountain Research Station, the Missoula Fire Sciences Laboratory. So Mark and Sarah, please take it away.
Well, hello, everybody. I would say good morning, but it's morning here in Missoula, Montana. I'm not sure what time it is where you're at, but I'm Mark Finney, research scientist here at the Forest Service. This is Sarah McAllister,
research mechanical engineer here.
And the two of us, along with a large team of people, study wildland fire in many different aspects. So we happen to study it from a physical science standpoint, understanding the behavior of fires. That is the energy release of the fires, how long they burn, how fast they burn, that kind of thing. But there's a lot of other scientists here at the lab that study ecological effects of fire, as well as smoke production, smoke effects on human health. So this fire lab is the biggest fire laboratory in the country. In fact, I think it's the biggest one in the world that's devoted to wildland fire. Wildland fire meaning it's different from structure fires, building fires or industrial fires, that kind of thing. So this laboratory has been in existence since 1960. Many different studies have gone on here, studying basic behavior of wildland fire, and that information has led to the development of models, computer models, mathematical models for predicting wildland fire that are used all over the country, in fact, all over the world. But these models were developed in 1960s and 1970s, and those models have a lot of limitations, a lot of assumptions to them. They're still very useful, but they don't actually tell us critical things about how fires spread, how fires behave. So Sarah and I can't really answer definitively how fires transfer heat from what's burning, what's the energy release rate, and how fuel particles ignite. Those are the three main factors in how fire spreads. So I'll say them one more time. How long fires burn and what's the energy release rate, how the heat is transferred from what's burning to new fuel particles, and then how those fuel particles heat up and ignite. Those are the three factors. We call it the circle of life, with apologies to the Lion King. We're still studying those aspects, and a little bit later in this broadcast, we're going to show some demonstrations mostly related to ignition. But first, what we thought we would do is give you a little bit of virtual tour of the fire lab and let you see the places where we work. Behind me is a wind tunnel, and in there you're seeing some flames that they're gas flames from propane burner. And what we use this for a lot of times is to study how convective heat transfer occurs. When I say convection, that is the movement of a fluid past an object, where the heat is transferred to the object or away from the object. So in this case, we're talking about very hot flames. They're about 1,000 degrees Celsius, and which is what? 1,600, about 1,600 Fahrenheit. So all flames are about that temperature, these kinds of flames anyway, and that includes forest fires. And the heat, the convective heat, that is when the flames touch an object, it heats that object up, and sometimes it heats it to ignition. Sarah's going to do a very nice demonstration about convective heating. There's another kind of heat, and that is radiation. Radiation is the kind of heat you feel on your face from the sun or on your hands from a campfire. It heats up your hands or your face without heating the air in between. So if you could feel the heat coming off of this fire, that would be radiation. So we're going to do a demonstration also with radiation in a little bit. So Josh here is going to add some gas to this flame so that what we can do is control the energy release rate. So the more energy that's released, the higher the flames. So when you're building a campfire, you want more flames, you add more wood to the fire, right? So you're increasing the amount of energy released from the fire. And wildland fires have a tremendous range of energy release, all the way from something that's very minor like this to flames that are maybe 100 meters tall. Okay, so this is burning in a wind tunnel that's 10 feet by 10 feet. And we can control the airflow that goes through here up to about 6 miles an hour, which doesn't sound like much, but you have a 6 mile an hour wind blowing in your face, that feels like a pretty strong wind. Okay, so maybe we can pan, thank you, Josh. Maybe we can pan back this direction here. Sarah and I will take a little walk through the wind tunnel area. So you're seeing on our right the big wind tunnel, the green wind tunnel. On the left is a small wind tunnel that can produce much higher velocities, maybe up to, what, 40 miles an hour?
Yeah, 40 miles an hour. That's right.
So we're going to walk down the hallway here into the control room. So remember that this laboratory was built in 1960. And in 1960, the way you controlled the airflow and the humidity and the temperature in all of the facilities was through controls like this. They have dials and they have manual controls, right? And we have printouts and readouts on paper, actually, to see what the temperature and humidity patterns are doing. So we can control the temperature and humidity, which are very important weather variables inside the facility here. Now, this is just a relic. It's just, it's been replaced with computer. Just a simple PC can control the entire operation. We have another facility that we can't go into right now that we'd like to show you, but we're going to point the camera over here. We're overlooking what's called the combustion chamber, which is a metal walled chamber that is 40 feet by 40 feet in horizontal dimensions, but 70 feet tall. So we can do a lot of experiments. You're seeing a lot of equipment being constructed right down there right now, and so that's why we can't go in there. But we can do a lot of experiments that don't require us to control the wind. So we can study how fire spreads on slopes or burn very large arrays of wood to study energy release rate, all the factors that go into fire behavior. Sarah, do you have anything to add?
To say that the big white thing down there is, in fact, the big test bed that we're building right now so we can look at fires on slopes in a pretty large scale for a lab.
So now I think we're going to move down the hall and we're going to do some demonstrations for you.
Yeah.
Hi.
That's the last thing that they're watching the door.
You see us? We're good. Gina, everything?
We hear you.
Okay.
All right. 1,500 degrees Celsius, or sorry, 1,500 degrees Fahrenheit. It's about 800 degrees Celsius. So here we're testing ignition by convection. So what Mark was talking about, it's really, really hot air that's going to heat up our fuels to ignition. And what's really interesting is that we see quite a bit of a difference when we go between heating due to convection versus heating due to radiation. So the way things ignite are different. So this is one of the things that we're learning, is to explore how the mode of heat transfer changes the way things ignite. So I've got a couple of demos here that I can show. And one of the really interesting things that we're learning is that depending on the mode of heat transfer really affects the way fuel particles ignite depending on their size. So we're going to do some tests here where we're looking at 2 different size fuels in convective heating, and then we're going to go over to a radiant heat panel and look at how those fuels ignite in the radiant heat. And we can compare and contrast the way the patterns of what happens. So here I've got a thick fuel particle. Hold up closer to the camera here so you can see it. It's about a ½ inch square. So I'm just going to stick this in and write hot air that's coming out of this white box right here. And we'll watch what happens. So you can see, if you can, zoom in a little bit more. It's heating up, and what looks like it's the edges that are heating up first, and then it ignites. But remember that it took, probably about 30 seconds or more to ignite. So let me take this out here, extinguish it. So for a comparison, I'm going to put in something much thinner. So here I've got just it's a very little stick, about 1/16 of an inch square. And this is much more like a wildland fuel, right? This is the kind of thing like that you would see as a needle or a small twig. And this is what usually carries the fire in wildland fires, right? Get my gloves back on here. These are fine. Getting my little clip. And it ignites much, much faster. One of the other things that we can do with this device is to study how actual live fuels ignite, right? So when you see all of the TV footage of big forest fires happening, often it's like the tree crowns themselves, the tops of the trees with all the live needles igniting. And what's really interesting about how that happens is that live fuels are living, they're breathing, they're photosynthesizing, and they are full of a lot of water. So the question is how could something that full of water possibly ignite and burn? It's just basically that's water. So we do other experiments where we take live fuels. So here I have just a little piece of a Doug fir, which is a very common tree that grows around here. It's involved in most of our fires. And I put this in here and torch our little live fuel. I don't know if you can hear that, but it makes quite a different noise than those little wood sticks that I was testing just a second ago. Do one more just in case. If you can't zoom in a little bit closer here. You can see it ignites in all sorts of crazy patterns because there's a lot of gases shooting out of it. So we think that's part of the puzzle of how live fuels can ignite, is that not only do they have water in them, but they have a lot of other things like sugars and starches that it's making from photosynthesis, and those are also flammable, and that's adding to the mix of things. So that's an active area of research that we're trying to figure out is what exactly is going on with live fuels. And do we have our radiant heater?
We are ready.
All right, so we're going to switch over to Mark and talk about radiant heat.
Thank you, Sarah. So Sarah's demonstration is very, very useful for examining how pure convective heating, that is hot air coming past particles, whether they're large particles or whether they're small particles, how it heats them up and ignites them, how long it takes those to ignite depending on their size and the temperature. But there's another way that heat is transferred from a fire to new fuels. Because wildland fire, if it's going to sustain itself, has to spread, has to move, it has to ignite new fuels all the time. So Sarah looked at convective heating. We also have radiant heating. Radiant heating, like we talked about, is the heat you feel on your face from the sun. Now we have a very simple demonstration here. This is a radiant panel. This is the kind of heater that you might find in a chicken heater, a chicken coop, or in a barn. And so just a commercial heater. This is putting out about 30 times, a little more than 30 times the energy that you feel on your face from the sun on a very, very hot sunny day. It's also about 10 times higher than what it would take to burn you. So 10 times greater than the amount of heat that your skin can take if exposed. So that's why I'm wearing gloves and I'm wearing this Nomex shirt that won't catch on fire. So one of the things that Sarah showed us was how the difference between large particles and small particles and how they respond to convective heat. Let's take a look at how they respond to radiant heat, okay? So this is the radiant panel. I'm going to put a large particle in front of this. This is the same particle that Sarah had. You see, I don't know, can you see that it's starting to smoke? You see that smoke coming off? So it started smoking almost immediately. Almost immediately. And the smoke is actually flammable. It's flammable gases coming off. And so if we take a lighter like this, we can actually light those gases in a minute and the thing will start to flame. So that took about 30 seconds or so. It took about the length of time that Sarah, it took about the same length of time as the large particle took in the convective heating. Let's take a look at what happens when we have a small particle. In this case, it's just a little, it looks like a pine needle, but it's a very thin piece of wood, about the same thickness as a pine needle. We're going to put that in front of this, okay? Let's see what happens. See a lot less smoke coming off of this one. In fact, in many experiments that we've conducted here and elsewhere, very rigorous experiments, you can find that these fine particles won't ignite from radiation. The reason is that they are cooling off. All this cold air around us is sufficient to cool them off. They're like they're suffering from wind chill. And so you know that if you're standing in a cold wind, the stronger the wind blows, the colder you feel. It's the same way with these small particles. They basically feel wind chill from all the cold air around, and they stay cool enough to where they don't ignite. So let's have a look at a couple other different kinds of particles. What we have here is, this is called Excelsior. It's 1 millimeter, it's shredded wood, it's 1 millimeter thick. And I have here a ball of Excelsior that is very compressed. I just compressed it with my hand. I have another nest of Excelsior, the same material, same amount, that's very loose. So we're going to take a look at how these two things respond to this radiant heat, okay? So I'm going to first put this compressed ball of Excelsior in front. Now, a little closer. You can start to see that this compressed ball of Excelsior is starting to smoke. And in a little bit, it's going to catch on fire, pretty much all by itself. Okay. Behind the scenes, Sarah is making sure we don't light our laboratory on fire. So this other, same Excelsior, same material, but very loose. Watch what happens when we put this in front. Actually, we could be here for quite a while, and we don't have the time to, but I'll just let it sit there. In fact, nothing's happening. See that? The demonstration that nothing happens when you put very loosely compacted material in front of a radiant source. And it's the same thing that's happening here as with the fine particles. Since there's so much cold air around these loose particles, they're able to cool off sufficiently and they don't heat up by radiation. So maybe that's kind of counterintuitive, right? Doesn't make a lot of sense. Same material, same moisture content, just that the compact fuels they can't cool off very well, and the loose fuels they can cool off very efficiently and they don't even start smoking. We could let them sit here all night and all day and nothing would happen. So this is a simple demonstration of the differences between radiation and convection and the response of fuel particles by size and compactness. And these are physical principles that are very important to how wildland fire spreads. Anything to add?
Good job.
So there's a lot of other aspects to wildland fire. Things we study here is the energy release rate from real fuels, from woody fuels or from duff or from pine trees. What does it take to generate this much heat or a lot of other heat? And for how long does that last? We still can't answer those questions very well because wildland fuels are highly variable. If you go out into the woods or out into the field, you notice that there are a lot of different species of plants in here. They're clumpy, they're spaced differently, there's different moisture contents, different sizes. So it's very difficult in a field setting to investigate the physics of how fire behaves and how these processes play out. So we'll be happy to answer any questions you've got.
Excellent. Thank you, guys. So if anyone has any questions, come on up to the microphone and the camera, and you can ask the scientists directly. Okay, so we're going to take our first question. Go ahead. Oh, you have to unmute your microphone.
That good?
Perfect.
Okay. We just finished studying biomes, and I'm wondering, like, all this stuff with the pine forest. Do you find that forests spread faster in like a pine forest, or something like we're in Pennsylvania? We're mainly a deciduous type forest. Do you find there's a difference in how fast they spread?
Yes, there are actually many differences between the fuel particles and how they're packed and how they're configured in pine forest compared to deciduous or broadleaf forest. Many differences there.
Or grass.
I'm sorry?
Grass. Very different.
And grass is very different. All these things are very different. And they change all of the factors in fire behavior, not just how fast fire spread, but they change the energy release rate, the heat transfer, and then the response of the fuel particles to heat transfer, whether it's radiation or convection. So all of the things in fire are affected by those different fuel properties. And I'll just say, and Sarah brings up a really good point. We would like to continue.
Oh, just fuels is only one part of the they call it wildfire behavior design, right? So fuels is definitely a part of the topography, where it is, what the fuels are, whether it's on a slope or a canyon, flat, open ground. That also affects how fire spreads, and also the weather. So wind, whether the humidity is high or whether the humidity is low, any kind of interaction between those variables all like how fast the fire spreads. So I mean, if everything is equal in a deciduous forest versus a coniferous forest, you're still going to get difference because of fuel, but often deciduous forests tend to be in, say, wetter places, particularly around here. We don't have a whole lot of deciduous trees except for when they're down by the creeks or something. So they're often a lot wetter and in little shady places, and so that's going to spread very differently for those aspects as well.
That's interesting because in our neighboring state in New Jersey, we have areas called the Pine Barrens, and there's forest fires every summer there, but it's rare to hear forest fires in where we directly live with the deciduous trees. So that's interesting. Thank you.
Great. Are there any other questions? I have a question. How did you get today? What was your?
We were getting feedback.
Did you all hear me?
Yes.
Yeah. So what was your career path? How did you get to where you are today?
So I'm a research forester, and my career path has been in forestry primarily, but with a kind of a physical science interest and in modeling fire behavior. So I began as a wildland firefighter in the old days when I was 19 years old, and I did that for 3 seasons, and then went to graduate school. I was very interested in fire ecology and fire behavior, and I went to graduate school and eventually worked on a PhD doing prescribed fire research and fire behavior modeling. So that was my career path.
I took a very different route. So when I was finishing high school, I didn't know what I wanted to do, but I knew I liked math and science. So I went and I did my undergraduate degree in mechanical engineering because it was a great application of math and science with having a very, very broad potential outlook, right? So a mechanical engineer do everything from designing roller coasters to heating and air conditioning systems in buildings to fire. So it was a very broad sort of job opportunity there to go into mechanical engineering. But as I was nearing my degree, I kind of realized that I didn't want to work for an engineering firm trying to build a widget for a customer or something. So I went to grad school. And that's where I kind of started down the path towards studying combustion and fire. And originally, my first direction into it was because I liked working on my car with my dad. So I spent all of my, from 16 on, with an old Volkswagen Beetle that I had to work on regularly with my dad. But I wanted to understand how it worked a little better. So went into combustion in grad school, started studying. My PhD was actually in understanding how materials burn in space. It was fun. It was actually funded by NASA. And then as part of the program, I actually had to take classes from an outside department. So I ended up taking classes in forestry because wildfires was pretty cool and an application to what I was studying in the engineering department. And then, yeah, got into the wildland fire field and took another turn and ended up here.
Excellent. We have a couple questions from YouTube. The first one is from Andrew Dorian's class in Winslow, Maine. And they want to know, is there a state when all factors are taken into consideration, so trees, weather, soil, moisture, etc., that has the lowest possible fire damage?
The lowest, what was the question?
Possible fire damage?
Yeah, what state has the lowest possibility of fire damage when you take into consideration trees, weather, soil, and moisture?
Well, that's easy. Antarctica.
I think they said not Alaska. Alaska doesn't count.
Well, Alaska actually has a lot of fires.
Yeah, so the thing is that there are many different factors that go into explaining wildland fire activity and fire behavior. Anywhere that's vegetated can have fire. We're seeing fires in Iceland now, we're seeing fires up in northern Scotland, and these are not human-caused fire. Not human-caused fires. Humans can carry fire and burn things that nature can't very often, because if you're talking about natural ignition sources, you're talking about lightning, you're talking about volcanoes, occasionally a rock slide, something like that, but it has to occur when things are dry, and it has to be a coincidence of ignition and dry conditions in fuel. But human beings have been responsible for most of the fire on the planet for about the last 500,000 years. And so anywhere there's vegetation, fire is there. Now you can talk about fire severity, I think is what the question was about, but it really depends on your perspective. So we often think that grass fires are not very severe because the landscape doesn't change very much after that. But if you are an ant or you're a piece of grass, then that fire is very severe. Okay? So from a human perspective, it doesn't appear severe, but from a plant perspective, it's just as severe as a crown fire is in, say, those New Jersey pine barrens.
At the same time, not all fires are necessarily damaging either. I mean, there are some forests that actually require some amount of fire to regenerate and reseed and regrow and be healthy. So,
and in fact, it's a very important point that we nationwide in the United States, we probably have too little fire under mild and moderate conditions now. Fire suppression has been very, very effective at controlling fires when they can be controlled, which what that does is build up the fuel and changes the fuel structure to the point when fires occurring under extreme conditions can't be controlled. So what science has showed us over the last century or so is very much what Sarah says, is the importance of fire in the ecology of most of our ecosystems.
All right, we have another question from YouTube. So it's students from Malu del Campo's class in Monterrey, Mexico. They'd like to know, what are the main factors that make wildfires so difficult to extinguish?
what are the main factors that make wildfires so difficult to extinguish?
Oh, well, so control of wildfires depends on many things. One big factor is how big it is. Once fires reach a certain size, it's pretty much impossible to put it out until the weather changes. So the other factors, at say a flame scale, at the scale that say Sarah and I would be fighting fire, is the intensity. If the fire is giving off so much heat and releasing so much energy, flames tend to be fairly tall, and it's too difficult for us to get close to those fires. And so you can't engage in a direct attack on a fire with very high intensity. In fact, the limit for that is about 4 feet. So if you see flames about 4 feet tall or less, then you can do a direct attack. And greater than that, you have to go indirect, back off to a ridge or build a fire line at some distance. Now, there's other factors that make fires difficult to suppress too, namely spotting. Okay, the wafting and transport of burning embers from the fire, ahead of the fire, landing in new fuels, and sometimes spotting can be many miles distant from the edge of the advancing fire. In Australia, it turns out that they have kind of the world record on spotting distance. It's something like 20 or 30 kilometers, so maybe 15 to 20 miles, because of the special eucalyptus bark that they have there under extreme conditions. So how fast the fire spreads, the spotting, the intensity, all these things make a big difference.
Excellent. We have a couple other questions from YouTube. One is from a high school student from Buena High School, New Jersey. They want to know, why does wind blow out fire even though fires need oxygen to stay lit?
Oh, okay. So the answer to that is because despite how it looks, the chemical reactions that generate fire take a little bit of time. So when the fuel comes in contact with the air, it takes a moment to actually produce a flame and combust. And if you interrupt that, they don't have time to actually burn. And that gets more and more pronounced if, say for example, if you're blowing it like a candle flame, your breath is actually cooling it too. So by cooling it, you're actually making it then take more time to then react. It took me till grad school and college to be able to.
Wood. You blew out the flame. You could reignite, right?
Right, because there's still fuel coming out of the wood.
Turning into gas.
Turning into
It's
gas,
still hot.
yes, it's still hot.
Right. So you can blow a flame out, but one of the reasons that you can't just take a big fan out to a forest fire and blow it out is that it's still very hot and you will reignite.
So something you can do that's for fun, next time you have a birthday or something, blow out your candles, but then while you still see that little bit of smoke, take another match and relight that smoke, because then it'll come back down and relight your candle. So that's a little fun thing you can probably do.
All right, we have some questions from our students in our G chat. So go ahead and ask away. You just need to unmute your microphone. Yep, you're good.
What is the most common reason that wildfires start?
What is the most common way for fires to start?
Yeah.
Oh, that's where you are. Mostly it's people, but out here in Montana, for example, there aren't that many people, and there's a lot of really remote areas down out in the woods and in the mountains and stuff where lightning is the primary cause, but most of it's people and accidental fires.
So in the eastern half of the United States, I would say about 80% of the fires are caused by people, maybe even higher in the northeast. In the southeast, it's probably about 80%. In the west, it's about 75% of the fires are caused by lightning.
Except for on July 4th.
Yeah, on July 4th, people play in the fire, right? Now, the big fires that you've heard about in California, those were all human-caused fires. They had origins of power lines and other kinds of accidental ignitions. But in general, if you just look at the fire statistics, most of the fires in the West, not necessarily the big ones, but most of the fires are caused by lightning in the East.
Thank you.
And what was your favorite experiment so far?
Well, my favorite experiment so far, we burned some very big fuel beds one day in the lab, and it got very, very hot, and may have accidentally melted the lights in there, like they were plastic. That was pretty fun, but we only did that twice.
My favorite experiments are field experiments, actually. We do most of our time, Sarah and I are in the laboratory doing experiments here. But we have to often go out to the field and do experiments at larger scales to test the physics that we find in the laboratory. So those are actually the most interesting. We go out and light fires in the forest or in the grass or in other fuel types and take measurements, the same kind of measurements we take in the lab, and we make comparisons. And if we get the same kinds of answers, we are then more confident that the physics we're finding in laboratory scales actually applies to the real scale out in the field where it matters.
Thank you.
Thank you. All right, you guys.
You're on mute.
Thank you. So our last question that we have from YouTube is, what are things that people can do in their communities to prevent wildfires from spreading?
There are many things that prevent wildfires from spreading. I think the most important aspect of that question would really be what's to prevent fires from damaging things we care about, right? And so the things that we care about a lot in communities are structures, our house, our infrastructure like power lines and bridges and phone lines and things like that. But in the wildlands, we care a lot about the watershed, the wildlife, the habitat, care a lot about timber supply. So all of these things need to be factored into how we deal with wildfire. And the most important thing you can do for your house is to clear away dead vegetation, keep flammable materials away from the structure itself, and do that on a routine basis. It's not just about what your house is made out of, it's how you maintain the area around it. And people call that defensible space. So it's a space around the house that's safe for firefighters to be so they can protect your house if you do get a wildfire. But then, very important, equally as important, is how we manage our wildlands. As we talked about earlier, most of our wildlands are fire adapted in some way. So if we use fire in a wise fashion, if we use other kinds of management activities, such as timber harvesting as well as prescribed burning, we can change the hazard. We can change the fuel complex such that you can't get severe fires. You can't get fires that are even threatening the community. So this is an important subject. It's a subject that the Forest Service and many communities are interested in now. And fortunately, science has provided a lot of good answers to how we deal with this. We just need to follow all of that information and actually implement it.
Excellent. Great. Well, that's all the time we have for today. So thank you so much, Sarah and Mark, for joining us and for being with us this morning, for sharing your time and your talent and your knowledge with us. And thank you to all of our students and teachers for joining us on this Tuesday morning after the long weekend. So if you're curious to learn more about the science behind wildfires, like last year's campfire, and to see Mark and Sarah on the big screen, you can stream NOVA's Inside the Mega Fire. That's on our website, pbs.org/NOVA. So thanks again, and we hope to see you all soon for a virtual field trip in the future. Have a great rest of your day.